The universe is a place of endless wonder, where every corner holds secrets we've only begun to uncover. Think about it. Out there, beyond our tiny blue planet, lies a tapestry of cosmic mysteries that defy explanation and push the boundaries of human understanding. From the invisible force of dark energy shaping the expansion of the universe to rogue planets drifting alone through the void, these are the questions that keep astronomers awake at night. Why? Because the answers don't just satisfy curiosity, they redefine what we know about reality itself. In this journey, we'll explore 30 of the most astounding cosmic mysteries, each one a puzzle piece in the grand story of existence. These aren't just scientific curiosities, they're gateways to understanding where we came from, where we're headed, and whether we're truly alone in the cosmos. So, buckle up, we're about to dive into the unknown, where every discovery challenges what we thought we knew and leaves us marveling at the sheer scale of the universe's secrets. Imagine looking out at the night sky and realizing that everything you see, every star, every galaxy, every speck of light, is being pushed apart by an invisible force. That force is dark energy, and it's one of the most profound mysteries in modern astronomy. Making up roughly 68% of the universe, dark energy is the dominant player in the cosmos, yet we can't see it, touch it, or even fully understand it. What we do know is this: it's causing the universe to expand, and not just expand, but to do so at an accelerating rate. This discovery, made in the late 1990s by teams observing distant supernova, turned our understanding of the universe upside down. Before this revelation, scientists assumed the universe's expansion would slow down over time, pulled by gravity. Instead, they found the opposite was true. Galaxies are racing away from each other faster and faster, as if propelled by some unseen hand. But what is dark energy? Is it a property woven into the very fabric of space itself, as Einstein once suggested with his cosmological constant? Or does it point to something entirely new, a force or principle that lies beyond our current grasp of physics? The implications are staggering. If dark energy is indeed a property of space, it means empty space isn't truly empty. It's brimming with energy, constantly stretching the universe apart. But if it's something else, it could rewrite the rules of gravity, challenging everything from Einstein's theory of relativity to our understanding of how the cosmos operates. For now, dark energy remains a tantalizing enigma, a puzzle that astronomers and physicists are working tirelessly to solve. It's a reminder that even in a universe filled with light, some of the most profound truths are hidden in the shadows. While dark energy is stretching the universe apart, there's another invisible force working in the opposite direction, holding everything together. Enter dark matter, the cosmic glue that keeps galaxies from flying apart. It's an invisible, mysterious substance that makes up roughly 27% of the universe, yet we can't see it, touch it, or even directly detect it. So how do we know it's there? The answer lies in its gravitational effects, which are impossible to ignore. Picture a galaxy spinning like a cosmic pinwheel. According to the laws of physics, the stars on the outer edges should be moving slower than those closer to the center. But observations tell a different story. Stars at the edges are moving just as fast, if not faster, than those near the core. The only explanation: there must be something massive, something unseen, exerting a gravitational pull strong enough to keep those stars in place. That something is dark matter. Without it, galaxies would simply fly apart, their stars scattering into the void. But what is dark matter? That's the million-dollar question. Scientists have proposed a range of possibilities, from weakly interacting massive particles, or WIMP, to exotic particles like actions. WIMP, for example, are hypothetical particles that rarely interact with ordinary matter, making them incredibly difficult to detect. Actions, on the other hand, are theorized to be ultra-light particles that could explain certain quirks in the universe. Yet, despite decades of searching, no direct evidence of dark matter has been found. The hunt for dark matter has taken scientists to some of the most extreme environments on Earth and beyond. Deep underground, in abandoned mines and tunnels shielded from cosmic radiation, detectors wait patiently for a rare interaction with a dark matter particle. In space, telescopes like the Hubble and the upcoming James Webb Space Telescope scan the skies for clues, mapping the distribution of dark matter by observing how it bends light from distant galaxies, a phenomenon known as gravitational lensing. Despite its elusive nature, dark matter's influence is everywhere. It's woven into the very fabric of the cosmic web, the intricate network of galaxies and clusters that spans the universe. Without it, the universe as we know it simply wouldn't exist. Yet, for all its importance, dark matter remains one of the greatest unsolved mysteries in science. It's a reminder that even in a universe filled with light, some of the most fundamental truths are hidden in the dark. And as we continue to search for answers, we're not just uncovering the secrets of the cosmos, we're rewriting the story of our existence. Now, let's turn our attention to a mystery that's pulling not just galaxies, but also the curiosity of astronomers worldwide, the Great Attractor. Picture this: our Milky Way, along with countless other galaxies, is racing through space at millions of kilometers per hour, all drawn toward a single, invisible point. This isn't just random motion, it's as if the universe itself has set its sights on a specific destination. But what lies at the end of this cosmic journey? That's the question at the heart of the Great Attractor, a gravitational anomaly so powerful it's reshaping our understanding of the universe's structure. Located roughly 250 million light-years away, the Great Attractor sits in a region of space obscured by the thick dust and stars of the Milky Way's galactic plane. It's like trying to peer through a dense fog, searching for something you know is there but can't quite see. What we do know is that it exerts an immense gravitational pull, one strong enough to influence the motion of entire galaxies, including our own. But what could possibly be massive enough to have such an effect? One leading theory suggests it's a supercluster of galaxies, a colossal gathering of thousands of galaxies bound together by gravity. The Norma cluster, for example, is thought to be part of this immense structure, contributing to the overall gravitational pull. But even this explanation falls short. The sheer scale of the Great Attractor's influence hints at something even more extraordinary, something that might challenge our current understanding of cosmic structures. Could it be the result of dark matter, that elusive substance we still struggle to detect? Or perhaps it's a sign of even larger structures in the universe, ones we've only begun to map. The truth is, we simply don't know yet. What makes the Great Attractor so fascinating is not just its mystery, but also what it reveals about the universe's interconnectedness. It's a reminder that even on the grandest scales, everything is in motion, pulled by forces we're only just beginning to comprehend. The challenge of studying the Great Attractor lies in its location. Hidden behind the Milky Way's galactic plane, it's shrouded in what astronomers call the zone of avoidance, a region so dense with stars, gas, and dust that traditional telescopes struggle to penetrate it. But that hasn't stopped scientists from trying. Using infrared and radio wavelengths which can cut through the obscuring material, researchers have begun to piece together a clearer picture of this enigmatic region. What they've found so far only deepens the mystery, revealing hints of structures and galaxies that could explain the immense gravitational pull, but also opening the door to even more questions. The Great Attractor isn't just a curiosity, it's a cosmic puzzle that challenges our understanding of how the universe works. It forces us to ask, what else is out there, hidden in the shadows of the cosmos? And how do these unseen forces shape the destiny of galaxies, stars, and even our own tiny corner of the universe? As we continue to explore, one thing is certain. The Great Attractor is a reminder that the universe is far stranger and far more interconnected than we ever imagined. Out in the depths of space, there are signals so brief and powerful they defy comprehension, bursts of energy that flash across the cosmos in less time than it takes to blink. These are fast radio bursts, or FRB, and they are one of the most perplexing mysteries in modern astronomy. First discovered in 2007, these signals pack an astonishing amount of energy into just milliseconds, often outshining entire galaxies in the process. But what's even more intriguing is where they're coming from, billions of light years away, far beyond the boundaries of our own galaxy. The mystery of FRBs lies not just in their intensity, but in their unpredictability. Some burst once and vanish without a trace, while others repeat at irregular intervals, offering tantalizing clues to their origins. One of the most famous repeating FRBs, known as FRB 1218, has been observed firing off bursts dozens of times, giving scientists a rare opportunity to study these enigmatic signals in detail. Yet, despite years of research, the true cause of FRBs remains shrouded in uncertainty. So, what could be producing these extraordinary bursts? One leading theory points to neutron stars, the dense remnants of exploded stars. Specifically, Magnetars neutron stars with incredibly strong magnetic fields are prime suspects. These cosmic powerhouses can unleash colossal amounts of energy, and some FRBs appear to originate from regions where magnetars are known to exist. But not all FRBs fit this explanation, leaving room for other possibilities. Could black holes be involved? Some astronomers speculate that FRBs might be the result of cataclysmic events, like the collision of two black holes or the destruction of a star by a black hole's immense gravity. These violent encounters could release bursts of energy detectable across vast distances. And then there's the more speculative and controversial idea: could FRBs be signals from an advanced extraterrestrial civilization? While this possibility captures the imagination, most scientists agree it's unlikely, given the sheer energy required to produce such bursts. Still, the idea adds an extra layer of intrigue to an already fascinating mystery. To unravel the secrets of FRBs, astronomers are using some of the most advanced tools at their disposal. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have revolutionized the search, detecting hundreds of FRBs in recent years. Each new detection brings us closer to understanding these cosmic flashes, but every answer seems to raise more questions. For instance, why do some FRBs repeat while others don't? And what can their unique properties tell us about the environments they originate from? What makes FRBs so captivating is not just their mystery, but what they reveal about the universe. These bursts travel billions of light years to reach us, passing through galaxies, gas clouds, and magnetic fields along the way. By studying how FRBs interact with the material they encounter, scientists can map the cosmic web, the vast, invisible structure that connects all matter in the universe. In a way, FRBs are like cosmic messengers, carrying information about the distant reaches of space and the forces that shape it. Yet, for all we've learned, FRBs remain a puzzle, a reminder of how much we still have to discover about the cosmos. They challenge us to think beyond the familiar, to consider possibilities that stretch the limits of our imagination. And as we continue to search for answers, one thing is certain: the universe is full of surprises, and FRBs are just the beginning. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and planets. Given the sheer scale, it seems almost inevitable that life, intelligent life, should exist somewhere out there. Yet, when we look up at the night sky, we're met with silence. No signals, no signs, no evidence of other civilizations. This glaring contradiction is at the heart of the Fermi Paradox, a question that has puzzled scientists and philosophers alike for decades. If the universe is so vast and ancient, where is everyone? Named after physicist Enrico Fermi, who famously posed the question during a casual lunchtime conversation in 1950, the Fermi Paradox forces us to confront a deeply unsettling possibility. With billions of potentially habitable planets in our galaxy alone, why haven't we encountered even a single trace of extraterrestrial intelligence? The silence of the cosmos is deafening, and it challenges some of our most fundamental assumptions about life and our place in the universe. One possible explanation is that intelligent life is extraordinarily rare. While the universe may be teeming with microbial life, the leap to complex, intelligent beings might require a perfect storm of conditions: stable planetary environments, long periods of geological stability, and the absence of catastrophic events like asteroid impacts or supernova. Even if these conditions are met, the development of technology and civilization might be an even rarer occurrence. In this scenario, Earth could be a cosmic fluke, a 1 in a trillion anomaly in an otherwise lifeless universe. But what if intelligent life is common, just fleeting? Another possibility is that advanced civilizations tend to self-destruct before they can make contact with others. Whether through war, environmental collapse, or technological disasters, the window of opportunity for interstellar communication might be incredibly narrow. This idea, often referred to as the Great Filter, suggests that there's a critical barrier, a point in the evolution of civilizations that's nearly impossible to surpass. If true, it raises a chilling question. Are we approaching our own Great Filter, or have we already passed it? Then there's the possibility that we're simply looking in the wrong way. Our search for extraterrestrial intelligence has largely focused on radio signals, a method that assumes other civilizations would use similar technology. But what if advanced beings communicate through methods we haven't even imagined? Perhaps they've moved beyond radio waves, harnessing quantum entanglement or other exotic technologies that are invisible to us. Or maybe they're deliberately avoiding contact, observing us from afar like a cosmic nature preserve. The Fermi Paradox doesn't just challenge our understanding of the universe, it forces us to reflect on ourselves. Are we alone, or are we just too young and inexperienced to recognize the signs of other civilizations? The answers we seek might not lie in the stars, but within our own capacity to imagine, explore, and survive. As we continue to search the cosmos, the silence we encounter may be less about the absence of others and more about the limits of our own understanding. And in that silence, there's a profound opportunity to redefine what it means to be human in a universe that might be far stranger and far more lonely than we ever imagined. Picture a planet adrift in the vast emptiness of space, untethered to any star, no sun to warm its surface or cast light on its landscapes. These are rogue planets, lonely worlds wandering the cosmos without a home. Unlike the planets in our solar system, which orbit the sun, rogue planets are nomads, traveling through the galaxy's dark expanses, guided only by the faint pull of gravity. And here's the astonishing part. There may be more of these rogue planets in the Milky Way than there are stars. So how do these solitary worlds come to exist? One possibility is that they were born in the chaos of a young star system. During the turbulent early days of planetary formation, gravitational interactions between planets could fling one or more worlds out of their orbits, sending them hurtling into interstellar space. Another theory suggests that some rogue planets might form on their own, collapsing directly from clouds of gas and dust, much like stars do, but without enough mass to ignite nuclear fusion. These wandering worlds challenge our traditional understanding of what a planet is. Without a star to anchor them, rogue planets exist in perpetual darkness, their surfaces likely frozen and barren. But could life still find a way to survive in such extreme conditions? It's not as far-fetched as it might seem. Some scientists speculate that beneath the icy crusts of these planets, geothermal heat or radioactive decay could create subsurface oceans, much like those believed to exist on Jupiter's moon Europa or Saturn's moon Enceladus. If that's the case, these hidden oceans might provide a haven for microbial life, thriving in the absence of sunlight. The discovery of rogue planets also raises intriguing questions about the diversity of planetary systems. If these free-floating worlds are as common as some estimates suggest, they could represent an entirely new class of celestial objects, one that we're only beginning to understand. In fact, astronomers have already detected a few of these elusive wanderers using techniques like gravitational microlensing, where the planet's gravity bends and magnifies the light from a distant star, revealing its presence. What makes rogue planets so fascinating isn't just their strangeness, but what they tell us about the universe's capacity for surprise. They remind us that the cosmos is far more varied and unpredictable than we often assume. While we've long thought of planets as stable, orderly members of star systems, rogue planets show us that the universe is full of exceptions to the rules, worlds that defy expectations and push the boundaries of what we consider possible. As we continue to explore the cosmos, these wandering worlds offer a tantalizing glimpse into the unknown. They challenge us to rethink our assumptions, to consider new possibilities, and to imagine what other secrets might be waiting out there in the dark. And who knows, perhaps one day we'll find that the universe's loneliest planets are also its most extraordinary. In the summer of 1977, a routine night of astronomical observation turned into one of the most intriguing moments in the history of the search for extraterrestrial life. It was August 15th, just past 10 o'clock at night, when a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary, a signal so powerful and unusual that it defied all expectations. For 72 seconds, the telescope recorded a burst of radio waves coming from the direction of the constellation Sagittarius, near a star called Chi Sagittarii. The signal was so intense that it dwarfed the background noise of the cosmos, and when astronomer Jerry Amon reviewed the data the next day, he circled the sequence and wrote a single word in the margin: wow. The WOW signal, as it came to be known, remains one of the most compelling pieces of evidence in the search for extraterrestrial intelligence. What made it so remarkable wasn't just its strength, but its frequency. The signal was detected at 1420 MHz, a frequency close to the hydrogen line, a natural emission frequency of hydrogen, the most abundant element in the universe. This frequency is often considered a logical choice for interstellar communication, as it's a universal marker that any advanced civilization might recognize. And yet, despite decades of searching, the signal has never been detected again. Was it a fleeting message from an alien civilization, or simply a cosmic coincidence? One of the most tantalizing aspects of the WOW signal is its brevity. 72 seconds might seem like a long time, but in the grand scale of the universe, it's the blink of an eye. If it was a deliberate transmission, why did it stop? Some speculate that the signal could have been a one-time broadcast, perhaps a beacon or a test signal from a distant civilization. Others suggest it might have been a natural phenomenon, like a comet or a burst of cosmic energy, that just happened to align perfectly with the telescope's observations. But even after ruling out many potential explanations, no definitive answer has been found. The mystery of the WOW signal has inspired countless theories and debates. Could it have been a message from a civilization far more advanced than our own, reaching out across the stars? Or was it a rare and fleeting cosmic event, a momentary blip in the vastness of space? The fact that we still don't know underscores just how challenging the search for extraterrestrial intelligence can be. It's like trying to find a needle in a haystack the size of the universe, where the needle might only appear for a fraction of a second. What makes the WOW signal so enduringly fascinating is not just the possibility of what it might have been, but what it represents, the hope that we're not alone in the cosmos. It's a reminder that even in a universe filled with unknowns, there's always the chance of discovering something extraordinary. And while the signal itself remains unexplained, it continues to inspire astronomers and dreamers alike to keep searching, to keep listening, and to keep asking the question, are we alone? For now, the WOW signal stands as a tantalizing enigma, a brief but powerful reminder of the universe's capacity to surprise us. Whether it was a message from the stars or simply a cosmic quirk, it challenges us to keep looking, to keep wondering, and to keep exploring the infinite possibilities that lie beyond our world. And in that sense, it's more than just a mystery, it's an invitation to imagine what else might be out there, waiting to be discovered. Far beyond the familiar planets and the icy realm of the Kuiper belt lies a mysterious, unseen frontier, a place so distant and faint that it exists more in theory than in observation. This is the Oort Cloud, a vast spherical shell of icy debris that encircles our solar system like a cosmic halo. Stretching nearly a light year from the Sun, it's a region so remote that it marks the very edge of our star's gravitational influence. And yet, despite its enormity, we've never directly seen it. The Oort Cloud remains one of the most elusive and intriguing mysteries in our cosmic backyard. Named after Dutch astronomer Jan Oort, who first proposed its existence in the 1950s, the Oort Cloud is thought to be a treasure trove of ancient, frozen relics from the earliest days of the solar system. Imagine a reservoir of comets, each one a time capsule preserving the raw materials that formed the planet's billions of years ago. These icy bodies, some no larger than a house and others as big as mountains, drift in the cold, dark expanse, occasionally nudged by gravitational forces into the inner solar system, where they become the spectacular long-period comets we sometimes see streaking across the night sky. But what exactly is the Oort Cloud made of, and how did it form? Scientists believe it's a remnant of the solar system's birth, a collection of icy debris left over from the chaotic process of planet formation. As the young Sun and its planets took shape, gravitational interactions with nearby stars and the Milky Way's tidal forces likely pushed these icy fragments into the distant reaches of space, where they've remained ever since. The Oort Cloud is essentially a frozen archive, preserving clues about the conditions and materials that existed when the solar system was just a swirling disk of gas and dust. Studying the Oort Cloud, however, is no easy task. Its distance makes it nearly impossible to observe directly, even with our most powerful telescopes. Instead, astronomers rely on indirect evidence, such as the trajectories of long-period comets like Hale-Bopp and Hyakutake, which are thought to originate from this distant region. By tracing the paths of these comets, scientists can infer the Oort Cloud's existence and begin to map its structure, but much about it remains unknown. How thick is this icy shell? How many objects does it contain? And what can it tell us about the forces that shaped our solar system? One of the most tantalizing possibilities is that the Oort Cloud might not be unique to our solar system. If other stars have their own versions of this icy frontier, it could mean that comets and the organic molecules they carry are common throughout the galaxy. This raises intriguing questions about the role of comets in seeding life. Could the icy bodies of the Oort Cloud have delivered water and essential building blocks to Earth billions of years ago? And if so, might they have done the same for other planets in the universe? The Oort Cloud is more than just a distant curiosity. It's a gateway to understanding our cosmic origins. Exploring this frozen frontier could reveal secrets about how planets form, how life begins, and how the universe itself is structured. It's a reminder that even the farthest reaches of our solar system hold stories waiting to be uncovered, stories that connect us to the very beginning of time. And as we continue to peer into the darkness, we're not just exploring the Oort Cloud, we're unraveling the history of our own existence. In the vast expanse of the solar system, where spacecraft glide silently through the void, even the smallest deviations from expected behavior can spark monumental questions. That's precisely what happened with Pioneer 10 and 11, two trailblazing probes launched in the early 1970s. These spacecraft were designed to explore the outer reaches of our solar system, but as they ventured farther from Earth, something strange happened. They began to slow down. Not just a little, but in a way that defied all predictions. This unexpected deceleration became known as the Pioneer Anomaly, a gravitational puzzle that has intrigued scientists for decades. At first glance, the anomaly might seem like a minor detail. After all, space is full of subtle forces: gravity from planets, pressure from sunlight, even the faint drag of interstellar dust. But what made the Pioneer Anomaly so perplexing was that none of these factors could fully explain the spacecraft's behavior. As the probes traveled beyond Saturn, they were found to be slowing down by a tiny but consistent amount, equivalent to about 1/10 billionth of the acceleration due to gravity on Earth. It was as if an invisible hand was gently tugging on them, pulling them back toward the sun. This discovery sent shockwaves through the scientific community. Could this be evidence of a new force of nature, one that hadn't been accounted for in our understanding of physics? Some speculated that it might hint at modifications to Einstein's theory of general relativity, or even the presence of dark matter in the solar system. Others suggested more exotic possibilities, like the influence of higher dimensions or undiscovered particles. The Pioneer Anomaly became a focal point for debates about the limits of our knowledge and the potential for groundbreaking discoveries. Over time, however, a more mundane explanation began to gain traction. Researchers proposed that the anomaly might be caused by thermal radiation, heat escaping unevenly from the spacecraft's power systems. As Pioneer 10 and 11 drifted farther from the Sun, their heat distribution could have created a subtle but measurable force, acting like a tiny thruster pushing against their motion. This theory seemed to fit the data, and for a while it appeared the mystery had been solved. But not everyone was convinced. Critics pointed out that the thermal explanation didn't fully account for the anomaly's magnitude, leaving room for lingering questions. Today, the Pioneer Anomaly remains a fascinating chapter in the history of space exploration, a reminder that even the most well-understood systems can hold surprises. While the thermal radiation theory has largely closed the book on the mystery for many scientists, it continues to inspire discussions about the precision of our measurements and the potential for hidden forces in the cosmos. It also highlights the importance of curiosity-driven science, where even the smallest anomalies can lead to profound insights. What makes the Pioneer Anomaly so compelling isn't just the mystery itself, but what it represents: the relentless pursuit of understanding in the face of the unknown. It's a testament to the ingenuity of scientists who refuse to let even the tiniest discrepancies go unexplained. And it's a reminder that the universe, vast and complex as it is, still has secrets waiting to be uncovered. As we continue to explore the cosmos, anomalies like this challenge us to look closer, think deeper, and never stop asking questions. Among the countless stars dotting the night sky, one stands out not for its brilliance but for its baffling behavior. Meet KIC 8462852, better known as Tabby's star. Located over 1,000 light-years away in the constellation Cygnus, this unassuming star has become the center of a cosmic mystery that's as perplexing as it is captivating. Unlike most stars, which shine with a steady, predictable glow, Tabby's star flickers erratically. its brightness dipping by as much as 22% at times, a fluctuation so extreme it defies all conventional explanations. What could possibly cause such dramatic changes? The answers, or lack thereof, have sparked one of the most intriguing debates in modern astronomy. When astronomers first noticed these strange dimming patterns in data from NASA's Kepler Space Telescope, they were stunned. Stars typically dim slightly when planets pass in front of them, but the dips caused by even the largest planets are minuscule, rarely exceeding 1%. Tabby stars' fluctuations, on the other hand, are massive and irregular, with no clear pattern or periodicity. At first, scientists considered the usual suspects. Maybe a cloud of dust or a swarm of comets was blocking the star's light. But these explanations fell short. The sheer scale and irregularity of the dimming events suggested something far more unusual was at play. Enter the alien megastructure hypothesis. In a bold and imaginative leap, some researchers proposed that the star's behavior could be the result of a Dyson sphere, a colossal structure built by an advanced extraterrestrial civilization to capture and harness the star's energy. First theorized by physicist Freeman Dyson in the 1960s, a Dyson sphere would consist of a vast network of solar panels or satellites encircling a star, effectively turning it into a cosmic power plant. If such a structure were partially completed or under construction, it could explain the erratic dimming patterns observed around Tabby's star. The idea captured the public's imagination, turning this distant star into a symbol of humanity's search for intelligent life beyond Earth. But before we pack our bags for Cygnus, it's worth noting that natural explanations are still very much on the table. Some scientists have proposed that the star's dimming could be caused by internal processes, such as massive star spots or magnetic activity, though these theories struggle to fully account for the observed data. Others suggest that a massive, uneven ring of dust or debris around the star might be responsible, possibly the remnants of a shattered planet or a colossal collision. While less exciting than the alien megastructure idea, these explanations remain grounded in the known laws of physics, and for now, they're the leading contenders. The mystery of Tabby's star is a testament to the power of curiosity and the allure of the unknown. It challenges us to think beyond the familiar, to consider possibilities that stretch the limits of our imagination. Whether the star's strange behavior is the result of alien engineering or an as yet unknown natural phenomenon, it reminds us that the universe is full of surprises. And as we continue to study this enigmatic star, we're not just searching for answers, we're expanding our understanding of what's possible in the cosmos. What makes Tabby's star so compelling isn't just the mystery itself, but the questions it raises about our place in the universe. Are we alone, or is there something or someone out there building structures on a scale we can barely comprehend? For now, the star remains a tantalizing enigma, a puzzle that invites us to keep looking, keep wondering, and keep dreaming about what might lie beyond the limits of our knowledge. And in that sense, Tabby's star is more than just a cosmic oddity. It's a beacon of possibility, shining brightly in the vast, uncharted expanse of space. Black holes have long been the ultimate cosmic enigmas, regions of space where gravity is so intense that not even light can escape. But beyond their awe-inspiring power, black holes pose a profound challenge to our understanding of the universe. At the heart of this challenge lies the black hole information paradox, a puzzle so perplexing it threatens to upend the very foundations of physics. Here's the problem. According to quantum mechanics, information is indestructible. Every particle, every interaction, every bit of matter carries information about its state, and that information should never disappear. It can change form, but it can't vanish. Black holes, however, seem to defy this rule. When matter falls into a black hole, it's crushed into a singularity, a point of infinite density. From our perspective outside the black hole, that matter, and the information it carries appears to be lost forever. This creates a glaring contradiction. How can information be preserved if black holes destroy it? This paradox has puzzled scientists for decades, and it's not just an abstract problem. The implications are enormous. If information truly disappears in black holes, it would mean that our understanding of quantum mechanics is incomplete, or worse, fundamentally flawed. Physicists have proposed several theories to resolve the paradox, but none have been definitively proven. One of the most famous ideas comes from Stephen Hawking, who theorized that black holes aren't entirely black. Instead, they emit a faint radiation now called Hawking radiation, as a result of quantum effects near the event horizon. Over time, this radiation could cause a black hole to lose mass and eventually evaporate. Hawking suggested that this process might somehow preserve the information, but exactly how remains unclear. Another compelling solution involves the holographic principle, a radical idea that suggests all the information about what falls into a black hole could be encoded on its surface. Imagine a black hole as a two-dimensional hologram projecting a three-dimensional reality. In this view, the information isn't lost, it's just stored in a way we don't yet fully understand. This idea has led to groundbreaking research in string theory and quantum gravity, but it's still far from being confirmed. The black hole information paradox isn't just a technical problem, it's a gateway to understanding the deepest mysteries of the universe. It forces us to confront the limits of our knowledge and ask questions that push the boundaries of physics. Are black holes truly the ultimate cosmic shredders, or is there a hidden mechanism that preserves information in ways we can't yet see? Could resolving this paradox lead us to a unified theory of quantum gravity, one that reconciles the seemingly incompatible laws of quantum mechanics and general relativity? For now, the paradox remains unsolved, a tantalizing reminder of how much we still have to learn about the cosmos. It's a testament to the power of science to challenge our assumptions and inspire us to explore the unknown. And as we continue to probe the mysteries of black holes, we're not just seeking answers, we're rewriting the story of the universe itself. The cosmic microwave background, or CMB, is often described as the oldest light in the universe, a faint glow left over from the Big Bang that permeates every corner of the cosmos. It's like a snapshot of the universe when it was just 380,000 years old, a time when the first atoms formed and light was finally able to travel freely. For decades, the CMB has been a treasure trove of information, helping scientists piece together the story of the universe's origins. But within this ancient light, there's a peculiar feature that defies explanation: the cold spot. Located in the constellation Eridanus, the cold spot is a region of the CMB that's significantly colder than its surroundings. At first glance, it might not seem like a big deal. After all, the universe is full of temperature variations. But the cold spot is different. Its temperature is so unusually low that it stands out as a glaring anomaly, one that challenges our understanding of the early universe. Is it just a statistical fluke, a random quirk in the data, or could it be evidence of something far more profound, like a parallel universe or a vast cosmic void? Let's break it down. The CMB isn't perfectly uniform. It's speckled with tiny fluctuations in temperature, each one reflecting the density variations of the early universe. These fluctuations are the seeds from which galaxies and galaxy clusters eventually grew. But the cold spot is an outlier. It's colder than it should be, even when accounting for the natural variations predicted by our current models. Some scientists have proposed that it might be the result of a cosmic void, a region of space so empty that it lacks galaxies, gas, and even dark matter. Light passing through such a void would lose energy, creating a cold spot in the CMB. But this explanation raises another question. How could a void so vast and empty have formed in the first place? Then there's the more speculative and mind-bending idea. The cold spot could be evidence of a collision with a parallel universe. According to some theories in multiverse cosmology, our universe might be just one of many, each existing in its own bubble of space-time. If another universe brushed against ours in the distant past, it could have left an imprint on the CMB like a cosmic fingerprint. This idea, while far from proven, has captured the imagination of scientists and the public alike, offering a tantalizing glimpse into the possibility of other universes beyond our own. Of course, not everyone is convinced. Some researchers argue that the cold spot is simply a statistical anomaly, a rare but natural variation in the CMB that doesn't require exotic explanations. After all, when you're studying something as vast and complex as the universe, anomalies are bound to pop up. But even if the cold spot is just a fluke, it's a reminder of how much we still have to learn about the cosmos. It challenges us to refine our models, question our assumptions, and explore new possibilities. What makes the cold spot so fascinating isn't just the mystery itself, but what it represents, the ongoing quest to understand the universe on the grandest scales. Whether it's a cosmic void, a parallel universe, or something else entirely, it's a reminder that the cosmos is full of surprises, and that even the oldest light in the universe can still hold secrets waiting to be uncovered. As we continue to study the CMB and probe the mysteries of the cold spot, we're not just exploring the universe, we're uncovering the story of our own existence, written in the faint afterglow of the Big Bang. And so, the cold spot remains one of the most intriguing puzzles in modern cosmology, a cosmic riddle that invites us to look deeper, think bigger, and imagine what else might be out there, hidden in the vast expanse of space and time. When we think of the universe's composition, the numbers can be mind-boggling. Dark energy makes up about 68%. Dark matter accounts for 27%, and ordinary matter, the stuff we're made of, fills in the remaining 5%. But here's the twist. Even that tiny sliver of ordinary matter, known as baryonic matter, isn't fully accounted for. In fact, about half of it is missing. This is the missing baryon problem, a cosmic puzzle that has left scientists scratching their heads for decades. If we can't even find half of the ordinary matter in the universe, what does that say about our understanding of the cosmos? Baryons are the building blocks of everything we can see and touch: protons, neutrons, and electrons. They form stars, planets, and even you and me. Yet, when astronomers tally up all the baryonic matter they can detect: stars, galaxies, gas clouds, they come up short. The numbers don't add up. Where could the missing baryons be hiding? One leading theory points to the vast, diffuse gas filaments that stretch between galaxies, known as the warm-hot intergalactic medium, or WIM. These filaments are incredibly difficult to detect because they're so thin and spread out, but they're thought to contain a significant portion of the missing matter. Imagine a cosmic spiderweb, invisible to the naked eye, threading its way through the voids of space, holding the universe together. But detecting the WIM is no easy task. It's like trying to find a whisper in a hurricane. Scientists have turned to powerful X-ray telescopes like NASA Chandra X-ray Observatory to hunt for these elusive filaments. By observing how X-rays are absorbed as they pass through the intergalactic medium, researchers can infer the presence of this hidden matter. Some studies have even claimed to detect hints of the WIM, but the evidence remains inconclusive. The challenge lies in the fact that the WIM is so diffuse and faint that even our most advanced instruments struggle to capture it. Another possibility is that the missing baryons exist in a form we haven't yet discovered. Could they be hiding in exotic states of matter, or perhaps in regions of space that are completely invisible to our current technology? Some theories suggest that these baryons might be tied up in low-mass objects like brown dwarfs or rogue planets, which are difficult to detect because they emit little to no light. Others speculate that the missing matter could be locked away in black holes or other dense objects, though this idea remains highly speculative. The missing baryon problem isn't just a scientific curiosity, it's a critical piece of the cosmic puzzle. Solving it would not only complete our picture of the universe's composition, but also provide insights into how galaxies form and evolve. After all, baryons are the raw materials for stars, planets, and life itself. If we can't account for half of them, it means there's a gap in our understanding of how the universe works on the grandest scales. What makes this mystery so compelling is the way it challenges us to think differently about the cosmos. It reminds us that even the most familiar elements of the universe, ordinary matter, can hold secrets that defy our expectations. As we continue to search for the missing baryons, we're not just filling in a gap in our knowledge, we're uncovering the hidden threads that weave the universe together. And in that search, we're reminded that the cosmos is far more complex and mysterious than we often assume. The cosmic microwave background, or CMB, is often hailed as the most detailed map of the early universe, a treasure trove of information about its infancy. But within this ancient light, there's something strange, a pattern so unexpected that it's been given a name straight out of a science fiction thriller, the axis of evil. This isn't a cosmic conspiracy, but a peculiar alignment of temperature fluctuations in the CMB that defies one of the most fundamental assumptions in cosmology, the idea that the universe is isotropic or the same in all directions. What could this mysterious alignment mean, and why does it have scientists so intrigued? At first glance, the CMB looks like a random patchwork of hot and cold spots, each one a snapshot of the density variations in the early universe. These fluctuations are the seeds from which galaxies and galaxy clusters eventually grew, and they're supposed to be randomly distributed with no preferred direction. But the axis of evil challenges this expectation. It's not just a random quirk, it's a statistically significant alignment of these fluctuations, suggesting that the universe might have a preferred direction, a cosmic north and south, if you will. This discovery has sent shockwaves through the scientific community, forcing cosmologists to rethink some of their most basic assumptions. So, what could cause such an alignment? One possibility is that it's a sign of new physics, something beyond our current understanding of the universe. Perhaps the laws of physics aren't as uniform as we thought, or maybe there's a hidden structure to the cosmos that we've yet to uncover. Some scientists have even proposed that the axis of evil could be evidence of a multiverse, a collision with another universe that left an imprint on our own. It's a bold idea, but one that's hard to rule out given the strange nature of this alignment. On the other hand, there's the simpler explanation. It could just be a statistical fluke. After all, when you're dealing with something as vast and complex as the universe, anomalies are bound to pop up. But the axis of evil isn't just a small blip in the data. It's a significant deviation from what we'd expect, making it harder to dismiss as mere chance. Some researchers have tried to explain it using existing models, suggesting that it might be the result of foreground contamination, dust or gas in our own galaxy distorting the CMB signal. But even these explanations struggle to fully account for the alignment's scale and significance. What makes the axis of evil so fascinating isn't just the mystery itself, but what it represents, a challenge to our understanding of the universe on the grandest scales. If the universe isn't isotropic, it could mean that our current models are incomplete or even fundamentally flawed. It's a reminder that even the most well-established theories can be upended by a single, unexpected discovery. And as we continue to study the CMB and probe the mysteries of the axis of evil, we're not just exploring the universe, we're pushing the boundaries of our own knowledge. For now, the axis of evil remains one of the most intriguing puzzles in modern cosmology, a cosmic riddle that invites us to look deeper, think bigger, and imagine what else might be out there, hidden in the vast expanse of space and time. Whether it's a sign of new physics, a statistical anomaly, or something else entirely, it's a reminder that the universe is full of surprises, and that even the oldest light in the cosmos can still hold secrets waiting to be uncovered. In the vast expanse of the cosmos, few objects shine as brilliantly or as mysteriously as quasars. Picture a light so intense that it outshines entire galaxies, a beacon so powerful that it's visible from billions of light years away. These extraordinary objects are not stars, nor are they ordinary galaxies. Instead, quasars are the blazing hearts of distant galaxies, powered by supermassive black holes at their centers. But what exactly are quasars, and how do they produce such staggering amounts of energy? The answers to these questions take us on a journey to the edges of our understanding, where the universe's most extreme forces collide. At the core of every quasar lies a supermassive black hole, a gravitational monster millions or even billions of times more massive than the Sun. But unlike the black holes we often imagine as dark, silent voids, these cosmic giants are anything but quiet. As matter spirals toward the black hole's event horizon, it forms an incredibly hot, swirling disk, a structure known as an accretion disk. Friction and gravity heat this disk to millions of degrees, causing it to glow with an intensity that can outshine thousands of galaxies combined. It's this process that transforms a supermassive black hole into a quasar, turning what should be an invisible object into one of the brightest phenomena in the universe. What makes quasars so fascinating isn't just their brilliance, but what they tell us about the early universe. Quasars are cosmic time capsules, relics from a time when the universe was young and chaotic. Most quasars existed billions of years ago, during an era when galaxies were still forming and black holes were feasting on vast amounts of gas and dust. By studying quasars, astronomers can peer back in time, uncovering clues about how galaxies evolved and how supermassive black holes grew to such colossal sizes. But this raises another question. How did these black holes become so massive so quickly in the universe's early days? One theory suggests that quasars may have formed through a process called hierarchical merging, where smaller black holes and galaxies collided and merged, feeding the growth of supermassive black holes. Another possibility is that quasars were fueled by enormous reservoirs of gas, drawn into the hearts of galaxies by gravity and funneled into their black holes. Whatever the mechanism, it's clear that quasars played a pivotal role in shaping the universe we see today. Their intense radiation and powerful jets of particles can influence star formation, heat surrounding gas, and even regulate the growth of entire galaxies. Yet, for all we've learned, quasars remain shrouded in mystery. How do they manage to channel such vast amounts of energy? What determines whether a supermassive black hole becomes a quasar or remains dormant? And why do some quasars seem to flicker on and off, as if their cosmic engines are sputtering? These questions remind us that quasars are not just distant curiosities, they're windows into the most extreme processes in the universe. Processes that continue to challenge and inspire us. As we study these cosmic beacons, we're not just uncovering the secrets of quasars, we're piecing together the story of the universe itself. They remind us that even in the farthest reaches of space, there are forces at work that defy our imagination, shaping the cosmos in ways we're only beginning to understand. And in that sense, quasars are more than just mysteries. They're a testament to the universe's boundless energy and the endless possibilities that await discovery. In the quest to understand the universe, one of the most fundamental questions we ask is, how fast is it expanding? The answer to this question isn't just a number, it's a key to unlocking the past, present, and future of the cosmos. But here's the twist. When scientists try to measure this expansion rate, known as the Hubble constant, they keep getting two different answers depending on the method they use. This discrepancy has become one of the most pressing mysteries in modern cosmology, and it goes by a name that reflects its perplexing nature, the Hubble tension. On one side of the equation, we have measurements based on the cosmic microwave background, or CMB, the afterglow of the Big Bang. By analyzing the faint ripples in this ancient light, scientists can calculate how fast the universe was expanding in its infancy and then extrapolate to the present day. These measurements suggest a relatively modest expansion rate, one that aligns with our best understanding of the universe's composition and evolution. But when astronomers turn to more local observations like the brightness of certain stars and supernova in nearby galaxies, they get a different result. These methods indicate that the universe is expanding faster than the CMB data predicts, and the difference isn't small. It's enough to make scientists question whether there's something fundamental we're missing. So, what's going on? Could it be that our measurements are flawed, or is there something deeper at play? One possibility is that our understanding of the universe's composition is incomplete. For decades, we've relied on a model that includes dark energy, dark matter, and ordinary matter to explain the cosmos. But what if there's an unknown ingredient, a new form of energy or particle that's influencing the expansion rate? Some theorists have proposed the existence of early dark energy, a mysterious force that may have altered the universe's expansion in its early stages, leaving a discrepancy that persists today. Others suggest that dark energy itself might be evolving over time, changing the rate at which the universe expands. Then there's the possibility that our measurements themselves are the issue. Measuring distances in space is incredibly challenging, and even the smallest errors can lead to significant discrepancies. For example, the brightness of certain stars and supernova used as standard candles to measure cosmic distances might not be as consistent as we once thought. Alternatively, there could be subtle biases in our observations that we haven't yet accounted for. The Hubble tension forces us to confront the limitations of our tools and methods, reminding us that even the most precise measurements in science are subject to uncertainty. What makes the Hubble tension so intriguing isn't just the mystery itself, but what it reveals about the process of discovery. Science thrives on discrepancies. They're the cracks in our understanding that lead to breakthroughs. Whether the tension is resolved by new physics, refined measurements, or something entirely unexpected, it's a reminder that the universe is always more complex than we imagine. And as we continue to explore this cosmic puzzle, we're not just searching for answers, we're pushing the boundaries of what we know about the cosmos and our place within it. The Hubble tension is more than a scientific challenge. It's a call to curiosity, a reminder that even the most fundamental questions can lead us to unexpected places. As we grapple with this mystery, we're reminded that the universe is full of surprises, and that every discovery brings us closer to understanding the grand story of existence. And in that sense, the Hubble tension isn't just a problem to solve. It's an invitation to keep exploring, keep questioning, and keep marveling at the wonders of the cosmos. Imagine stumbling upon a galaxy so faint, so ghostly, that it's almost invisible against the backdrop of space. Now picture this: despite its dim glow, this galaxy is as large as our Milky Way. These are ultra-diffuse galaxies, or some of the most mysterious objects in the cosmos. Unlike the bright, star-filled galaxies we're used to seeing, UDGs are vast, sprawling structures with surprisingly few stars. How can something so massive be so faint? And what does their existence tell us about the universe's grand tapestry of galaxy formation? Let's dive into this cosmic riddle. At first glance, ultra-diffuse galaxies seem to defy logic. They're enormous, often spanning tens of thousands of light years, yet they contain only a tiny fraction of the stars found in galaxies like our own. To put it in perspective, the Milky Way has hundreds of billions of stars, while a typical UDG might have just a few 100 million, a staggeringly low number for something of its size. This faintness makes them incredibly difficult to detect, which is why they've only recently come to the attention of astronomers. But now that we've found them, they're raising more questions than answers. One leading theory suggests that ultra-diffuse galaxies might be failed galaxies, cosmic underachievers that never managed to form many stars in the first place. In the early universe, galaxies are thought to grow by pulling in gas, which then collapses to form stars. But in the case of UDGs, something might have gone wrong. Perhaps they formed in regions with too little gas, or maybe their star-forming material was stripped away by the intense radiation of nearby galaxies. Without enough gas to fuel star formation, these galaxies would have remained dim and diffuse, frozen in a state of cosmic adolescence. Another intriguing possibility is that UDGs are the remnants of more typical galaxies that lost their gas through interactions with others. Imagine a galaxy wandering too close to a larger neighbor, its gas ripped away by gravitational tides or blasted out by supernova explosions. Over time, such a galaxy would lose its ability to form new stars, leaving behind a faint, ghostly shell of its former self. This idea is supported by observations of some UDGs that appear to reside in dense galaxy clusters, where such interactions are more likely to occur. But not all ultra-diffuse galaxies are found in these environments, leaving room for other explanations. There's also the question of dark matter. Most galaxies, including our own, are thought to be embedded in vast halos of this mysterious substance, which provides the gravitational glue holding them together. But UDGs challenge this assumption. Some ultra-diffuse galaxies seem to have surprisingly little dark matter, while others appear to have an abundance. What's going on here? Could these galaxies have formed in a way that bypassed the usual dark matter requirements? Or are we missing something fundamental about how dark matter behaves in these extreme environments? What makes ultra-diffuse galaxies so fascinating isn't just their faintness, but what they reveal about the diversity of the universe. They remind us that galaxies come in all shapes, sizes, and states of being, some bright and bustling, others dim and diffuse. By studying these ghostly objects, we're not just learning about UDGs, we're uncovering the many pathways a galaxy can take in its cosmic journey. They challenge our assumptions, push the boundaries of our models, and invite us to rethink what we know about the universe's grand design. As we continue to explore these enigmatic galaxies, one thing is certain: they're a testament to the universe's capacity for surprise. Whether they're failed galaxies, stripped remnants, or something entirely new, ultra-diffuse galaxies are a reminder that the cosmos is full of mysteries waiting to be unraveled. And in their faint, ghostly glow, we find a new perspective on the vast and varied story of galaxy formation, a story that's still being written, one discovery at a time. High above us, invisible to the naked eye, a constant rain of high-energy particles pours down from the depths of space. These are cosmic rays, tiny but incredibly powerful messengers from the far reaches of the universe. Traveling at nearly the speed of light, they carry with them secrets about some of the most extreme environments in the cosmos. But despite over a century of study, one fundamental question remains unanswered. Where do these cosmic rays come from? This enduring mystery has puzzled scientists for generations, and solving it could unlock new insights into the universe's most violent and energetic events. Cosmic rays were first discovered in the early 20th century, and their detection marked a turning point in our understanding of the universe. Unlike the steady glow of starlight or the predictable paths of planets, cosmic rays are chaotic and unpredictable. They're made up of protons, electrons, and even atomic nuclei, all racing through space with unimaginable energy. When these particles collide with Earth's atmosphere, they create a cascade of secondary particles, some of which we can detect on the ground. But tracing their origins back to their sources has proven to be a monumental challenge. One of the leading candidates for the origin of cosmic rays is supernova, the explosive deaths of massive stars. When a star goes supernova, it releases an enormous amount of energy, accelerating particles to nearly the speed of light. These accelerated particles could then escape into space, becoming the cosmic rays we detect. Observations of supernova remnants, like the famous Crab Nebula, show evidence of particle acceleration, lending support to this theory. But while supernovae are certainly powerful enough to produce some cosmic rays, they might not account for the highest energy particles, which carry energies millions of times greater than anything we can produce in particle accelerators on Earth. This leads us to another possible source: black holes. Specifically, the supermassive black holes at the centers of galaxies are thought to be cosmic ray factories. As matter spirals into these black holes, it forms jets of particles that shoot out at nearly the speed of light. These jets can stretch for millions of light years, and the particles within them could be accelerated to the extreme energies needed to produce the most powerful cosmic rays. Some of the highest energy cosmic rays detected on Earth appear to come from the direction of active galactic nuclei, where supermassive black holes are actively feeding, adding weight to this idea. But the mystery doesn't end there. Some cosmic rays might originate from even more exotic sources, like gamma-ray bursts, the most energetic explosions in the universe, or even the collisions of galaxy clusters. These events are so powerful that they could easily accelerate particles to the extreme energies we observe. Yet, pinpointing the exact sources of these cosmic rays is incredibly difficult, partly because their paths are bent by magnetic fields as they travel through space, making it nearly impossible to trace them back to their origins with precision. What makes cosmic rays so fascinating isn't just their mysterious origins, but what they reveal about the universe. These particles are like cosmic detectives, carrying clues about the environments they've passed through and the events that accelerated them. By studying them, we can learn about the magnetic fields of distant galaxies, the structure of supernova remnants, and even the nature of dark matter. Yet, for all we've learned, cosmic rays remain one of the longest-standing puzzles in astrophysics, a reminder that the universe is full of questions waiting to be answered. As we continue to explore the origins of cosmic rays, we're not just solving a scientific mystery, we're uncovering the story of the universe's most extreme environments. Whether they come from supernova, black holes, or something even more exotic, cosmic rays remind us that the cosmos is a place of boundless energy and endless discovery. And in their journey across the universe, they invite us to keep searching, keep questioning, and keep marveling at the wonders of the cosmos. When a massive star reaches the end of its life, it doesn't fade quietly into the cosmic night. Instead, it goes out with a bang, a supernova explosion so powerful it can outshine entire galaxies. But what's left behind is no less extraordinary: a neutron star, one of the most bizarre and fascinating objects in the universe. Picture a star with the mass of our Sun, crushed into a sphere no larger than a city. The result is an object so dense that a single teaspoon of its material would weigh billions of tons. Yet, despite their small size, neutron stars are cosmic powerhouses, offering us a glimpse into the most extreme physics nature has to offer. So, what exactly lies beneath the surface of a neutron star? The answer is anything but simple. At their core, neutron stars are thought to be composed primarily of neutrons particles that, under normal circumstances, are found tucked safely inside atomic nuclei. But in the intense gravitational crush of a neutron star, These neutrons are packed together so tightly that they form a state of matter unlike anything we can replicate on Earth. Some scientists speculate that this environment might give rise to even stranger forms of matter, such as quark-gluon plasma, a primordial soup of subatomic particles that existed just moments after the Big Bang. In this exotic state, the boundaries between protons and neutrons dissolve, leaving behind a sea of quarks and gluons, the fundamental building blocks of matter. But the possibilities don't end there. Some theories suggest that neutron stars might be hiding something even more extraordinary: strange stars. These hypothetical objects would be composed of strange matter, a form of matter made up of strange quarks, a heavier, more unstable cousin of the quarks found in ordinary matter. If strange stars exist, they could represent a completely new class of celestial objects, one that challenges our understanding of how matter behaves under extreme conditions. The idea is both tantalizing and speculative, but it underscores just how much we still have to learn about these cosmic enigmas. Neutron stars aren't just curiosities, they're cosmic laboratories, offering us a unique window into the laws of physics under conditions we can't possibly recreate on Earth. Their immense gravitational fields, for example, allow us to test Einstein's theory of general relativity in ways that would otherwise be impossible. And their rapid rotation, some neutron stars spin hundreds of times per second, gives us insights into the behavior of matter at unimaginable speeds. But perhaps most intriguing of all is the possibility that neutron stars could be harboring secrets about the very nature of matter itself. What makes these stars so captivating isn't just their extreme properties, but the questions they raise about the universe. Are they the ultimate endpoint of stellar evolution, or do they represent a stepping stone to even more exotic objects? Could they hold clues about the early universe when matter existed in forms we can barely comprehend? As we continue to study neutron stars, we're not just exploring the remnants of dead stars, we're probing the boundaries of our understanding, uncovering secrets that could reshape our view of the cosmos. In the end, neutron stars are more than just dense remnants of supernova. They're cosmic puzzles waiting to be solved. And as we delve deeper into their mysteries, we're reminded that the universe is a place of endless wonder, where even the smallest objects can hold the biggest surprises. Whether they are made of neutrons, quarks, or something even stranger, neutron stars challenge us to think beyond the familiar and imagine what else might be out there, hidden in the depths of space. In the vast and varied cosmos, few objects are as extreme or as enigmatic as magnetars. Picture a neutron star, already one of the densest and most bizarre objects in the universe, and then give it a magnetic field so powerful it could strip the information from every credit card on Earth from thousands of miles away. That's a magnetar, a cosmic powerhouse with a magnetic field a quadrillion times stronger than Earth's. But what makes these objects so extraordinary, and what can they teach us about the universe's most extreme environments? At their core, magnetars are a type of neutron star, the collapsed remains of a massive star that exploded in a supernova. But unlike ordinary neutron stars, magnetars are born with a twist, literally. During the supernova explosion, the star's core collapses and spins faster and faster, like a figure skater pulling in their arms. If conditions are just right, this rapid rotation can generate a magnetic field of unimaginable strength. The result is an object so magnetic it can distort the very fabric of space-time around it, creating ripples that echo across the cosmos. But the real drama begins when a magnetar unleashes its energy. These stars are known for producing some of the most powerful bursts of radiation ever observed, including gamma-ray flares and X-ray pulses. In just a fraction of a second, a magnetar can release more energy than the sun emits in 100,000 years. These outbursts are so intense that they can be detected from billions of light years away, lighting up the universe like cosmic fireworks. Yet, despite their ferocity, magnetars are incredibly rare. Fewer than 30 have been confirmed in our galaxy, making them some of the most elusive objects in the cosmos. So, what drives these explosive events? One leading theory points to the magnetar's crust, a solid outer layer that's under unimaginable stress. As the star's magnetic field twists and shifts, it can cause the crust to crack, releasing massive amounts of energy in the process. Think of it like an earthquake, but on a cosmic scale, a starquake. These starquakes can trigger the powerful bursts of radiation that magnetars are known for, offering a glimpse into the turbulent life of these magnetic monsters. But magnetars aren't just fascinating for their explosive behavior. They are also cosmic laboratories offering insights into the limits of physics. Their intense magnetic fields push the boundaries of what's possible, creating conditions so extreme that they challenge our understanding of matter and energy. For example, in the presence of such a strong magnetic field, atoms themselves are stretched into long, thin shapes, completely unlike the familiar structures we see on Earth. This bizarre state of matter, known as magnetized matter, is unlike anything we can recreate in a lab, making magnetars invaluable for testing the laws of physics under the most extreme conditions. What makes magnetars so captivating isn't just their power, but what they reveal about the universe. They remind us that the cosmos is a place of endless extremes, where the rules we take for granted on Earth can be bent, broken, or rewritten entirely. By studying these magnetic marvels, we're not just exploring the remnants of dead stars, we're uncovering the secrets of the universe's most extreme environments. And in their explosive bursts and twisted magnetic fields, we find a new perspective on the forces that shape the cosmos, forces that continue to challenge and inspire us. As we continue to explore the mysteries of magnetars, one thing is certain: these cosmic powerhouses are more than just curiosities. They're windows into the universe's most extreme physics, offering clues about how matter behaves under conditions we can barely imagine. And in their magnetic fury, we find a reminder that the universe is full of surprises, waiting to be discovered by those who dare to look deeper. What lies ahead for the universe? Will it stretch endlessly into an infinite void? Or will it one day collapse back in on itself in a dramatic reversal of the Big Bang? This is one of the most profound questions in cosmology, and it hinges on a delicate cosmic tug of war between two opposing forces, dark energy and gravity. Each of these forces plays a critical role in shaping the destiny of the cosmos, and understanding their interplay could reveal whether the universe is destined for eternal expansion or a fiery collapse. Let's start with dark energy, the mysterious force driving the universe's accelerating expansion. Discovered in the late 1990s, dark energy makes up a staggering 68% of the universe's total energy content, and its influence is only growing stronger. Think of it as a kind of cosmic repulsion, pushing galaxies apart faster and faster over time. If dark energy continues to dominate, the universe will expand indefinitely, growing colder and darker as galaxies drift farther and farther apart. Stars will burn out, black holes will evaporate, and eventually the cosmos could reach a state known as the Big Freeze, where the universe becomes a vast, empty expanse of near absolute zero temperatures. But dark energy isn't the only player in this cosmic drama. Gravity, the force that binds galaxies, stars, and planets together, acts as a counterbalance, pulling matter inward and resisting the expansion. In the early universe, gravity was the dominant force, slowing the expansion caused by the Big Bang. Even today, it continues to shape the universe on smaller scales, holding galaxies and galaxy clusters together. But could gravity ever regain the upper hand? Some theories suggest that if dark energy weakens over time, gravity might eventually reverse the universe's expansion, pulling everything back into a big crunch. In this scenario, the universe would collapse into an incredibly dense, hot state, potentially setting the stage for another Big Bang, a cyclical universe with no beginning or end. The fate of the universe, then, depends on the balance between these two forces. If dark energy remains constant or grows stronger, the universe will continue to expand forever. But if gravity gains the upper hand, the cosmos could face a dramatic collapse. The challenge for scientists is figuring out which of these forces will ultimately prevail. Observations of distant supernova, galaxy clusters, and the cosmic microwave background all provide clues, but the data is still far from conclusive. What we do know is that the answer lies in the precise nature of dark energy, a mystery that continues to elude us. This cosmic question isn't just about the universe's future, it's about our place within it. If the universe is destined for eternal expansion, it raises profound questions about the ultimate fate of life and consciousness. Will intelligent beings in the far future, if they exist, be able to survive in a universe growing colder and emptier by the second? On the other hand, a collapsing universe would bring its own existential challenges, as galaxies, stars, and planets are crushed together in a fiery finale. Either way, the fate of the cosmos is a reminder of how small and fleeting our existence is in the grand scheme of things. What makes this mystery so captivating isn't just the science, but the philosophical weight it carries. It forces us to confront the limits of our knowledge and the vastness of the unknown. Are we living in a universe that will expand forever, or one that will one day collapse in on itself? The answer lies in the delicate balance between dark energy and gravity, two forces that continue to shape the cosmos in ways we're only beginning to understand. As we peer into the distant future, we're not just exploring the fate of the universe, we're uncovering the story of our own existence, written in the stars. Imagine an explosion so powerful it unleashes more energy in a few seconds than the sun will emit over its entire 10 billion-year lifetime. These are gamma-ray bursts, or to be brief, intense flashes of gamma radiation that light up the universe like cosmic fireworks. Detected by satellites as fleeting blips of energy, these bursts are among the most energetic events ever observed. But what could possibly trigger such colossal explosions? The answer lies at the intersection of life, death, and the universe's most extreme physics. Gamma-ray bursts come in two main flavors, short and long. Short bursts last less than 2 seconds and are thought to originate from the collision of two neutron stars, ultra-dense remnants of supernova. When these stellar corpses spiral into each other, they release a titanic burst of energy, along with ripples in space-time known as gravitational waves. Long bursts, on the other hand, can last several minutes and are believed to stem from the collapse of massive stars. When a star many times more massive than the Sun exhausts its fuel, its core collapses into a black hole, triggering a supernova and launching jets of material at nearly the speed of light. These jets, focused into narrow beams, produce the intense gamma-ray flashes we detect across the cosmos. But even with these theories, the origins of gamma-ray bursts remain shrouded in mystery. For one, not all bursts fit neatly into these categories. Some exhibit hybrid features, blurring the lines between short and long bursts and leaving scientists scratching their heads. Then there's the question of how these bursts produce such staggering amounts of energy. The processes involved are so extreme that they push the limits of what we know about physics, requiring conditions that are almost impossible to replicate on Earth. It's like trying to understand a hurricane by studying a drop of water. Adding to the intrigue is the fact that gamma-ray bursts are incredibly rare. In a galaxy the size of the Milky Way, a burst might occur only once every million years. Yet because they're so bright, we can detect them from billions of light years away, making them invaluable tools for studying the distant universe. When a burst is detected, telescopes around the world swing into action, capturing its afterglow in visible light, X-rays, and radio waves. These observations provide clues about the burst's environment, helping scientists piece together the story of its origins. One of the most fascinating aspects of gamma-ray bursts is their potential connection to life itself. Some theories suggest that long bursts could sterilize entire galaxies, making them uninhabitable for life as we know it. On the flip side, the same bursts might also play a role in seeding the universe with heavy elements like gold and platinum, forged in the fiery aftermath of neutron star collisions. It's a cosmic paradox. These bursts could both create and destroy the building blocks of life, shaping the universe in ways we're only beginning to understand. What makes gamma-ray bursts so captivating isn't just their power, but what they reveal about the universe's most violent and transformative events. They're like cosmic messengers carrying information about the birth of black holes, the death of stars, and the formation of elements. Yet, for all we've learned, they remain one of the greatest mysteries in astrophysics, a reminder that the universe is full of extremes we can barely comprehend. As we continue to study these enigmatic bursts, we're not just uncovering the secrets of gamma-ray flashes, we're exploring the very limits of what's possible in the cosmos. And in their fleeting brilliance, we find a glimpse of the universe's boundless energy and the forces that shape its destiny. Let's shift our focus from the dark, all-consuming depths of black holes to their cosmic opposite, white holes. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their event horizon, white holes are theorized to be the cosmic fountains, spewing out matter and energy in a dramatic reversal of their dark counterparts. But here's the catch: while black holes are well documented and studied, white holes exist only in the realm of theory, predicted by the same equations of general relativity that describe black holes. White holes remain one of the most intriguing and elusive mysteries in modern physics. So, what exactly is a white hole? Imagine a black hole running in reverse. Instead of matter and light being pulled inward, never to escape, a white hole would expel matter and energy outward, creating a region of space-time where nothing can enter, only exit. It's like a cosmic one-way door, but in reverse. The idea is mind-bending, but it emerges naturally from the mathematics of Einstein's theory of general relativity. In fact, white holes are mathematically just as valid as black holes. They're essentially the time-reversed version of them. But while black holes are supported by overwhelming observational evidence, white holes have never been detected, leaving scientists to wonder if they're real or just a fascinating quirk of the equations. One of the most compelling theories about white holes is that they could be the other side of black holes. Some models suggest that a black hole could connect to a white hole through a theoretical tunnel in space-time called a wormhole. In this scenario, matter falling into a black hole might not be lost forever, but instead emerge from a white hole in another part of the universe, or even in another universe entirely. It's a tantalizing idea, one that bridges the gap between science and science fiction. But without observational evidence, it remains purely speculative. So, why haven't we found a white hole? The challenge lies in their very nature. If white holes expel matter and energy, they'd likely be incredibly bright and energetic, making them hard to miss. But the universe is full of bright, energetic phenomena, from quasars to gamma-ray bursts, and none of them have been definitively linked to white holes. Another hurdle is that white holes are thought to be highly unstable. Unlike black holes, which can form and persist over billions of years, white holes might only exist for a fleeting moment before collapsing or transforming into something else. This instability could make them nearly impossible to detect, even if they do exist. Despite the lack of evidence, white holes continue to captivate scientists and science enthusiasts alike. They challenge our understanding of space-time, forcing us to consider the possibility of cosmic processes that defy our everyday intuition. They also raise profound questions about the nature of the universe itself. Could white holes be part of a larger cosmic cycle, where matter and energy are recycled through black holes and white holes in an endless loop? Or are they simply a mathematical curiosity, a what-if scenario that will never be observed? What makes white holes so fascinating isn't just their theoretical nature, but what they represent, the boundary between what we know and what we can only imagine. They remind us that the universe is full of possibilities, some of which might lie forever beyond our reach. And as we continue to explore the cosmos, white holes stand as a testament to the power of curiosity, a reminder that even the most outlandish ideas can lead us to deeper insights about the nature of reality. Whether they exist or not, white holes challenge us to think bigger, to push the boundaries of our understanding, and to keep asking the questions that drive science forward. Beyond the familiar orbits of Neptune and Pluto lies a region of the solar system that's anything but ordinary, a vast, icy expanse teeming with dwarf planets, comets, and other small, icy bodies. But there's something strange happening out there. The orbits of these distant objects seem to be tugged and twisted by an unseen force, as if something massive is lurking in the shadows. Could this be the elusive Planet 9, a hidden world waiting to be discovered, or is it something else entirely? This cosmic mystery has astronomers on the edge of their seats, as the search for this hypothetical planet could rewrite the story of our solar system. The first hints of Planet 9's existence came from the peculiar behavior of trans-Neptunian objects, or icy bodies that orbit the Sun far beyond Neptune. In the early 21st century, astronomers noticed that some of these objects shared a strange trait. Their orbits were clustered in a way that couldn't be explained by the known planets alone. Instead, it seemed as though an unseen object, perhaps 10 times the mass of Earth, was subtly pulling on them, guiding their paths through the outer solar system. This observation sparked a bold idea. Could there be a 9th planet, one we've yet to detect? But finding a planet in the distant reaches of the solar system is no easy task. Unlike the planets closer to the Sun, which reflect plenty of sunlight and are relatively easy to spot, a potential Planet 9 would be incredibly faint. It would orbit so far from the Sun, perhaps 20 times farther than Neptune, that it would receive barely any light, making it nearly invisible to our telescopes. To make matters worse, its orbit could take anywhere from 10,000 to 20,000 years to complete, meaning we'd only catch a tiny fraction of its journey across the sky. It's like trying to find a needle in a cosmic haystack. Despite the challenges, scientists have been relentless in their search. Using computer simulations, they've mapped out possible orbits and predicted where Planet 9 might be hiding. Telescopes like the Subaru telescope in Hawaii have scanned the skies, searching for faint glimmers of light that could reveal the planet's location. So far, the hunt has turned up empty, but that hasn't dampened the excitement. Every new piece of data brings us closer to solving the puzzle, and the possibility of discovering a new planet in our own backyard is too tantalizing to ignore. Of course, not everyone is convinced that Planet 9 is the answer. Some astronomers argue that the strange orbits of TNOs could be explained by other factors, like the collective gravitational pull of smaller objects or even the influence of a passing star long ago. Others suggest that our understanding of gravity itself might need revisiting, though this is a more radical and less favored explanation. The debate is far from settled, and it's this uncertainty that makes the mystery so compelling. What makes the search for Planet 9 so fascinating isn't just the possibility of finding a new world, but what it reveals about the complexity of our solar system. Even after centuries of exploration, there are still secrets hiding in the farthest reaches of our cosmic neighborhood. Whether Planet 9 turns out to be a massive planet, a swarm of smaller objects, or something entirely unexpected, its discovery, or lack thereof, could reshape our understanding of how the solar system formed and evolved. As we continue to probe the outer edges of our cosmic home, the mystery of Planet 9 reminds us that there's always more to discover. It's a testament to the power of curiosity and the relentless pursuit of knowledge, even in the face of uncertainty. And while the search may take years or even decades, the journey itself is a reminder that the universe is full of surprises, waiting to be uncovered by those who dare to look deeper. Whether Planet 9 is out there or not, it's a story that captures the imagination and keeps us looking to the stars, wondering what else might be waiting to be found. Among the countless celestial bodies in our solar system, none captivates us quite like the Moon. Its serene glow has inspired poets, guided explorers, and even regulated the rhythms of life on Earth. But for all its familiarity, the Moon holds a deep, ancient secret, its origin. How did this luminous companion come to be? The answer lies in a cataclysmic event that not only shaped our planet but also set the stage for life as we know it. This is the mystery of the Moon's formation, a story of cosmic collisions, planetary rebirth, and the delicate balance that makes Earth unique. The leading theory, known as the giant impact hypothesis, paints a dramatic picture. Around 4.5 billion years ago, the early Earth was a chaotic place, still cooling from its fiery formation. During this turbulent time, a Mars-sized object, often referred to as Theia, hurtled toward our planet. The collision was unimaginably violent, releasing energy equivalent to trillions of atomic bombs. Theia's impact didn't just strike Earth, it obliterated both bodies, sending molten debris hurtling into space. Over time, this debris coalesced under gravity, forming the Moon we see today. But while this theory elegantly explains many of the Moon's characteristics, it's not without its challenges. For one, the chemical composition of the Moon is strikingly similar to Earth's, particularly in the isotopes of oxygen found in lunar rocks. If the Moon formed from a mix of Earth and Theia, why doesn't it show more of Theia's unique signature? Some scientists propose that Theia might have had a composition nearly identical to Earth's, an unlikely but not impossible scenario. Others suggest that the impact was so intense it thoroughly mixed the two bodies, erasing any trace of Theia's distinct chemistry. Another puzzle lies in the Moon's orbit. The giant impact hypothesis predicts that the Moon should have formed with a tilted orbit, but its current path aligns almost perfectly with Earth's equator. How did it settle into such a stable position? One possibility is that the Moon's orbit evolved over time, influenced by gravitational interactions with Earth and the Sun. This process, known as tidal evolution, could have gradually aligned the Moon's orbit, but the details are still being worked out. Despite these lingering questions, the giant impact hypothesis remains the most compelling explanation for the Moon's formation. And its implications go far beyond the Moon itself. The collision likely stripped Earth of its early atmosphere, allowing a new one to form. One rich in nitrogen and oxygen, perfect for supporting life. The impact also tilted Earth's axis, creating the stable seasons that have shaped the evolution of plants, animals, and humans. In a very real sense, the Moon's formation wasn't just a cosmic accident. It was a pivotal moment in the story of life on Earth. What makes this mystery so fascinating isn't just the science, but the way it connects us to the cosmos. The Moon isn't just a distant object in the sky, it's a piece of Earth's history, a reminder of the violent processes that shaped our world. As we continue to study lunar rocks, simulate ancient collisions, and probe the Moon's secrets, we're not just uncovering the story of our celestial neighbor, we're learning about the forces that made life possible. And in that journey, we find a deeper appreciation for the delicate, interconnected dance of the universe, a dance that began with a single, world-altering impact billions of years ago. The Sun, our closest star, the source of light and life for our planet, holds a mystery that has baffled scientists for decades. At first glance, it seems straightforward. The Sun's surface, or photosphere, glows at a scorching 5,500 degrees Celsius. But here's the twist. Its outer atmosphere, the corona, is even hotter, reaching temperatures of over 1 million degrees Celsius. How can the corona, which is millions of kilometers away from the Sun's core, be so much hotter than the surface? This temperature inversion defies everything we know about heat transfer and has become one of the most enduring enigmas in solar science. To understand why this is so puzzling, let's take a step back. Normally, heat flows from hotter regions to cooler ones. Think of a campfire. The flames are hottest at the center, and as you move outward, the temperature drops. The Sun, however, flips this logic on its head. The corona, despite being far from the Sun's core, is hundreds of times hotter than the surface. It's like standing next to a bonfire and feeling the air around you get hotter the farther you step away. A scenario that makes no sense under conventional physics. So, what's going on? One leading theory points to the Sun's magnetic field as the key player. The Sun is a seething ball of plasma, a state of matter where electrons are stripped from atoms, creating a chaotic, electrically charged environment. This plasma interacts with the Sun's magnetic field, generating intense energy. Some scientists believe that tiny, explosive events called nanoflares could be heating the corona. These are like miniature solar flares, releasing bursts of energy that, when added up, might account for the corona's extreme heat. However, direct evidence of nanoflares has been elusive, leaving this theory in the realm of educated speculation. Another possibility involves magnetic waves known as Alfvén waves, which ripple through the Sun's plasma like vibrations on a guitar string. These waves could carry energy from the Sun's surface into the corona, where it's deposited as heat. Think of it as a cosmic version of shaking a rope to create waves that travel upward, transferring energy along the way. While this idea is compelling, the exact mechanisms by which these waves heat the corona remain unclear, and the math behind it is incredibly complex. Then there's the role of magnetic reconnection, a process where the Sun's magnetic field lines break and reconnect, releasing vast amounts of energy. This phenomenon is well documented in solar flares, but whether it's the primary driver of coronal heating is still up for debate. The challenge lies in observing these processes in action. The corona is a dynamic, ever-changing environment, and capturing the precise moments when energy is transferred is no easy feat. What makes the mystery of the Sun's corona so fascinating isn't just the scientific challenge, but its real-world implications. The corona isn't just a cosmic curiosity. It's the source of the solar wind, a stream of charged particles that flows outward, influencing space weather and affecting everything from satellites to power grids on Earth. Understanding how the corona works could help us predict solar storms, which have the potential to disrupt communications and even pose risks to astronauts. As we continue to study the Sun with advanced telescopes and spacecraft like NASA's Parker Solar Probe, we're inching closer to solving this puzzle. Each new observation brings us a step closer to understanding how the Sun's corona defies the laws of conventional physics. And in that pursuit, we're reminded that even the most familiar objects in the universe can hold secrets that challenge our understanding and inspire us to explore further. The Sun, our constant companion in the sky, continues to shine not just with light, but with mysteries waiting to be unraveled. Beyond the orbit of Neptune, far from the warmth of the Sun, lies a vast and icy realm known as the Kuiper belt. This distant region, stretching billions of kilometers into the outer reaches of our solar system, is home to a treasure trove of frozen worlds, dwarf planets, and ancient remnants from the dawn of our cosmic neighborhood. But the Kuiper belt isn't just a collection of icy debris, it's a time capsule preserving clues about how the solar system formed over 4.5 billion years ago. What secrets does this frozen frontier hold, and what can it tell us about our place in the universe? The Kuiper belt is often compared to the asteroid belt between Mars and Jupiter, but it's far larger and more mysterious. While the asteroid belt is made up mostly of rocky bodies, the Kuiper belt is dominated by icy objects, some of which are as large as small planets. Pluto, once considered the 9th planet, is the most famous resident of this region, but it's far from alone. Dwarf planets like Eris, Haumea, and Makemake also call the Kuiper belt home, each one a frozen world with its own unique story to tell. These icy bodies are remnants of the early solar system, left over from the chaotic process that formed the planets we know today. One of the most fascinating aspects of the Kuiper belt is its role in shaping the solar system. Scientists believe that the gravitational pull of Neptune played a key role in sculpting this region, scattering icy bodies into their current orbits and creating the intricate dance of objects we see today. Some of these bodies, like Pluto, are in stable, resonant orbits with Neptune, while others follow more erratic paths. This dynamic interplay between planets and smaller objects offers a glimpse into the gravitational forces that shaped the solar system's infancy. But the Kuiper belt isn't just a relic of the past, it's also a source of ongoing discovery. In recent years, missions like NASA's New Horizons have ventured into this distant region, providing unprecedented views of its inhabitants. The spacecraft's flyby of Pluto in 2015 revealed a world far more complex and dynamic than anyone had imagined, with icy mountains, vast plains, and even a thin atmosphere. And in 2019, New Horizons visited another Kuiper belt object, Arrokoth, a bizarre, snowman-shaped body that offered clues about how planets and other objects formed from tiny particles in the early solar system. What makes the Kuiper belt so intriguing isn't just its icy inhabitants, but what they can teach us about the origins of life. Many of these objects are rich in organic molecules, the building blocks of life, preserved in their frozen state for billions of years. Could these icy bodies have delivered water and organic materials to Earth, seeding our planet with the ingredients for life? It's a tantalizing possibility, one that underscores the importance of studying this distant region. As we continue to explore the Kuiper belt, we're not just uncovering the secrets of our solar system's past, we're also gaining insights into the processes that shape planetary systems across the galaxy. This frozen frontier reminds us that the universe is full of surprises, waiting to be discovered by those who dare to look beyond the familiar. And in its icy depths, we find a connection to our cosmic origins, a story written in the frozen remnants of a time long before the Earth was born. Now, let's take a leap into one of the most mind-bending questions in all of science. Could our universe be just one of countless others? This is the mystery of the multiverse, a concept that stretches the boundaries of our imagination and challenges everything we think we know about reality. Imagine a cosmic tapestry woven not just from one universe, but from an infinite number of them, each with its own unique set of physical laws, constants, and even dimensions. It's a staggering idea, one that forces us to reconsider not just the nature of existence, but also our place within it. The multiverse theory didn't emerge from science fiction. It grew out of the necessity to explain some of the deepest puzzles in physics. Take, for example, the fine-tuning of the universe. Our cosmos seems to have been perfectly calibrated to allow life to exist. The fundamental constants of nature, like the strength of gravity or the charge of an electron, are precisely balanced in a way that makes stars, planets, and ultimately life possible. But why does the universe have these specific values? the multiverse theory offers a tantalizing answer. Maybe there are countless universes out there, each with different constants, and we just happen to live in one where the numbers work in our favor. One of the most compelling versions of the multiverse idea comes from inflationary cosmology, a theory that describes the rapid expansion of the universe just moments after the Big Bang. According to this model, our universe isn't the only bubble of space-time that inflated. There could be an infinite number of others, each with its own unique properties. In some of these universes, gravity might be weaker or atoms might not form at all. In others, the laws of physics could be so different that life as we know it would be impossible. It's a dizzying thought, but one that helps explain why our universe seems so finely tuned. Then there's the concept of the quantum multiverse, which arises from the strange and counterintuitive world of quantum mechanics. In this view, every time a quantum event occurs, like the decay of an atom or the flip of a particle spin, the universe splits into multiple versions, each representing a different outcome. In one universe, Schrödinger's famous cat might be alive. In another, it's dead. This idea, known as the many worlds interpretation, suggests that every possible outcome of every event is realized somewhere in the multiverse. It's a radical departure from our everyday experience, but it offers a way to make sense of the probabilistic nature of quantum physics. But how could we ever test such a speculative idea? After all, if other universes exist, they're likely beyond our ability to observe directly. Some scientists have proposed that we might find indirect evidence, like imprints of collisions between our universe and others in the cosmic microwave background, the faint afterglow of the Big Bang. Others suggest that the multiverse could leave subtle clues in the behavior of particles or the distribution of galaxies. While these ideas are still in their infancy, they represent the first steps toward exploring a concept that once seemed purely philosophical. What makes the multiverse so captivating isn't just the science, but the questions it raises about the nature of reality. If there are infinite universes, does that mean there's a version of you reading this script in a parallel reality? Could there be a universe where the laws of physics allow for phenomena we can't even imagine? And if the multiverse is real, what does that say about the uniqueness of our own existence? These are questions that blur the line between science and philosophy, challenging us to think beyond the confines of our observable universe. While the multiverse remains a speculative idea, it's a powerful reminder of how much we still have to learn about the cosmos. It pushes us to question our assumptions, explore new possibilities, and embrace the vastness of the unknown. Whether or not we ever find evidence of parallel universes, the multiverse theory invites us to dream bigger, to imagine a reality far more complex and wondrous than we've ever imagined. And in that sense, it's not just a mystery, it's an invitation to keep exploring, keep wondering, and keep reaching for answers in the infinite expanse of the cosmos. Time is one of those things we all take for granted until we stop to think about it. Why does it always move forward? Why can't we rewind it like a tape or pause it altogether? These questions might seem simple, but they touch on some of the deepest mysteries in physics and cosmology. What exactly is time, and why does it have a direction? This is the mystery of time, a puzzle that has puzzled scientists and philosophers for centuries. At its core, time is one of the four dimensions that make up the fabric of space-time, a concept introduced by Einstein's theory of relativity. Unlike the three spatial dimensions length, width, and height, time has a unique property. It flows in one direction from the past to the future. This one-way flow is often referred to as the arrow of time, and it's one of the most fundamental aspects of our experience of reality. But why does time have an arrow? Why can't it go backward or stand still? One of the key ideas that helps explain the arrow of time comes from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases over time. Think of a cup of coffee cooling down or an ice cube melting. These processes are irreversible, and they illustrate how the universe naturally moves toward greater disorder. This increase in entropy gives time its direction, creating a clear distinction between the past and the future. In the past, the universe was more ordered. In the future, it will be more chaotic. It's a simple yet profound insight, but it raises even more questions. Why was the universe so ordered in the first place? And what does this mean for the ultimate fate of time itself? Some scientists believe the answer lies in the Big Bang. At the very beginning, the universe was in an incredibly low entropy state, packed with energy and potential. As it expanded and cooled, entropy began to increase, setting the arrow of time in motion. But this only pushes the mystery further back. Why was the early universe so ordered? Some theories suggest that our universe might be part of a larger multiverse, where the conditions of the Big Bang were just one possibility among many. Others propose that time itself might have a more complex structure, with multiple arrows or even loops that we can't yet comprehend. Then there's the question of whether time is real or just an illusion. In the equations of physics, time often appears as just another dimension, no different from space. Yet our experience of time, the way it flows, the way it shapes our lives, feels profoundly different. Could time be an emergent property, something that arises from the interactions of particles and forces, rather than a fundamental feature of the universe? It's a radical idea, but one that's gaining traction among some physicists. If true, it would mean that time as we know it is a kind of cosmic mirage, a byproduct of deeper, more fundamental processes. What makes the mystery of time so captivating isn't just the science, but the way it connects to our everyday lives. Time shapes everything we do, from the rhythm of our days to the trajectory of our lives. Yet, despite its ubiquity, it remains one of the least understood aspects of the universe. As we continue to explore this enigma, we're not just uncovering the secrets of time, we're grappling with the very nature of existence. And in that journey, we're reminded that some of the most profound mysteries are the ones that seem the most ordinary, like the steady, unrelenting flow of time itself. As we peer into the vastness of space, one question looms larger than any other. Are we alone? This is the mystery of life in the universe, a quest that spans from the dusty plains of Mars to the distant exoplanets orbiting stars light years away. It's a question that doesn't just drive scientific exploration, it challenges us to rethink what life is, where it can exist, and what it means to be alive in the cosmos. And while the search for extraterrestrial life has yet to yield definitive answers, every discovery brings us closer to understanding whether Earth is a cosmic rarity or just one of countless homes for life in the universe. Let's start close to home with Mars, our planetary neighbor, and one of the most promising candidates for finding life beyond Earth. For decades, robotic explorers like the Curiosity and Perseverance rovers have scoured the red planet, searching for signs of past or present life. Mars wasn't always the barren desert it is today. Billions of years ago, it had flowing rivers, lakes, and possibly even oceans. Could life have emerged in those ancient waters? Evidence of organic molecules and methane in the Martian atmosphere has sparked excitement, but the question remains, are these signs of life or just the result of geological processes? The search continues with future missions like NAS, a Mars sample return aiming to bring Martian rocks back to Earth for closer examination. But Mars is just the beginning. Beyond our solar system, the hunt for life has expanded to exoplanets, worlds orbiting other stars. Thanks to missions like NASA, Kepler, and TESS, we've discovered thousands of these distant planets, some of which lie in the habitable zone. the region around a star where temperatures could allow liquid water to exist. Water, as we know, is essential for life as we understand it, and finding it on another world would be a game changer. Exoplanets like Proxima Centauri b, just over 4 light-years away, and the TRAPPIST-1 system with its 7 Earth-sized worlds have become prime targets in this cosmic search. But habitability isn't just about water. It's about the right combination of atmosphere, chemistry, and stability. Could any of these distant worlds host life or even civilizations? The search for extraterrestrial life isn't limited to planets either. Moons like Europa orbiting Jupiter and Enceladus circling Saturn have captured scientists' attention. Beneath their icy surfaces, vast oceans of liquid water are thought to exist, kept warm by the gravitational tug of their host planets. Europa's subsurface ocean, for example, might contain twice as much water as all of Earth's oceans combined. Could microbial life thrive in these dark, hidden seas? The upcoming Europa Clipper mission aims to find out, using advanced instruments to study the Moon's ice shell and search for signs of habitability. Yet, the search for life isn't just about finding it, it's about defining it. What if life elsewhere doesn't look like anything we've seen on Earth? Scientists are exploring alternative biochemistries, imagining forms of life that might use silicon instead of carbon or ammonia instead of water. These possibilities push the boundaries of our understanding, reminding us that life might be far more diverse and adaptable than we've ever imagined. It's a humbling thought. The universe might be teeming with life, but in forms so alien we don't even recognize them. What makes this mystery so compelling isn't just the science, but what it says about us. The search for extraterrestrial life is at its core a search for connection, a desire to understand our place in the cosmos. Are we a cosmic fluke or part of a grander tapestry of life stretching across the stars? Every discovery, from the faintest flicker of a distant exoplanet to the faintest trace of methane on Mars, brings us closer to answering that question. And in that journey, we're reminded that the universe isn't just a place to explore, it's a story to be told. One that challenges us to imagine the unimaginable and dream beyond the limits of our world. As we continue to search the cosmos, we're not just looking for life, we're uncovering the story of existence itself. And whether we find it on Mars, in the icy oceans of Europa, or on a distant exoplanet light years away, the discovery will change everything. It will remind us that we're part of something far greater, a universe filled with endless possibilities and mysteries waiting to be solved. The search for life isn't just a scientific endeavor, it's a journey of wonder, curiosity, and hope, one that keeps us looking to the stars and asking, are we alone? As we wrap up this cosmic journey, it's impossible not to feel a sense of awe at the sheer scale of the mysteries we've uncovered. From the invisible grip of dark energy to the ghostly wanderings of rogue planets, each enigma we've explored has pushed the boundaries of what we thought we knew. These aren't just scientific puzzles, they're invitations to dream bigger, to look deeper, and to question the very fabric of reality. They remind us that the universe is not a static place, but a dynamic, ever-evolving tapestry of wonder waiting to be unraveled. What makes these mysteries so captivating is not just their complexity, but the way they connect us to the cosmos. Each discovery, each unanswered question, is a thread in the grand story of existence, a story that stretches back to the Big Bang and forward into an uncertain, exhilarating future. Whether it's the flickering light of a distant quasar or the faint echo of a gamma-ray burst, every piece of the puzzle adds to our understanding of where we came from, where we're going, and what lies beyond the horizon of our knowledge. But the journey doesn't end here. In fact, it's only just beginning. With every new observation, every breakthrough in technology, we're peeling back another layer of the universe's secrets. Telescopes like the James Webb Space Telescope are giving us unprecedented views of the cosmos, while missions to Mars, Europa, and beyond are bringing us closer to answering age-old questions about life beyond Earth. The tools we have today are more powerful than ever, and the discoveries they're enabling are reshaping our understanding of the universe in ways we couldn't have imagined just a few decades ago. And yet, for all we've learned, the cosmos remains a place of infinite mystery. The more we discover, the more questions arise, each one deeper and more profound than the last. This is the nature of science, not to provide all the answers, but to keep asking better questions. It's a journey of curiosity, of wonder, and of relentless exploration, driven by the belief that there's always more to learn, more to discover, and more to marvel at. So, as we close this chapter, let's not think of it as an ending, but as a beginning. The stars above are not just points of light, they're beacons calling us to explore, to question, and to imagine. The mysteries of the universe are not just challenges for scientists, they're invitations for all of us to look up and wonder. Whether you're an astronomer, a dreamer, or simply someone who loves to gaze at the night sky, the cosmos has something for you. It's a reminder that we're part of something vast, something beautiful, and something profoundly mysterious. The universe is out there, waiting to be explored. What will we find next? The answers are written in the stars, and they're ours to uncover. So keep your eyes on the sky, your mind open to the unknown, and your heart full of curiosity. After all, the greatest mysteries are the ones that inspire us to keep searching, keep dreaming, and keep reaching for the stars. The cosmos is calling. What will you discover? If this journey through the cosmos has sparked your curiosity, don't let the adventure end here. Hit that like button, share this video with fellow space enthusiasts, and subscribe to join us as we continue to explore the universe's most captivating mysteries. From the enigmatic whispers of dark matter to the explosive brilliance of gamma-ray bursts, the cosmos is brimming with stories waiting to be told, and we're just getting started. What cosmic mystery keeps you up at night? Is it the eerie glow of Tabby's star, the haunting silence of the Fermi Paradox, or the mind-bending possibility of parallel universes? Drop your thoughts in the comments below. We'd love to hear which celestial enigma fascinates you the most. Let's keep the conversation alive and dive deeper into these cosmic wonders together. The universe is vast, mysterious, and endlessly inspiring. So, until our next cosmic exploration, keep your eyes on the stars, your mind open to the unknown, and your heart full of wonder. The cosmos is calling, and there's so much more to discover. Thanks for watching, and remember, the universe is not just out there, it's a story we're all a part of. See you